Okay. I think it's recording now.
Yeah, it
Okay,
shows recording.
can you see my screen?
Yeah.
Okay, good. Let me start. Okay. So, last time we spoke about method of moments and likelihood estimation, and today I'll talk about Bayesian estimation, and I'll discuss briefly what is the relationship between likelihood estimation and Bayesian estimation. Okay, so uh, and we did one property of invariance, property of maximum likelihood estimation. Okay, now so if you look into the likelihood estimation, typically likelihood estimation, what happens is if you have x tilde, say x1, x2, xn, some IID with some from some function f of x with some parameter theta. Theta belongs to some parameter space capital theta, and it's unknown. Our main target is to learn or estimate theta from the data. Okay, from the given the data, we want to learn the theta. This is a typical problem of statistics, whereas in the probability, if generally it is assumed we know the value of theta, then what is the chance certain values of x will appear? This is typically so. Like in the direct probability problem, we try to solve the opposite problem. Okay. Now, in the standard likelihood estimation, what happens is typically it is being assumed that theta is constant. Okay. Theta is constant. And so what people do, people just write down the likelihood function L theta given x tilde, which is typically the xi given theta, and then theta hat MLE is argument of maximum of L theta given x tilde. Okay, so over the search goes on over theta. So this is typical the likelihood estimates that we try to solve. Now, what happens in Bayesian, but at the, even if it is constant, I mean, typical frequentist method, typical frequentist method is saying theta is unknown constant, but some kind of continuous variable, typically continuous variable. Okay. For example, when you are assuming that x tilde follows a Bernoulli P, you are saying P is between 0 and 1. So we know that the true value of P is some kind of constant, but the P itself is a some kind of text value, continuous value between in this range 0 to 1. And given the data, we try to make a likelihood estimates, try to find the value of P for which the likelihood is maximum. So that is what typically do. Or if you have, say, x tilde followed by say normal mu sigma square, then it is a two-dimensional space. In that case, we assume mu is between minus infinity and infinity, and sigma square or sigma is between 0 to infinity, and we try to find using likelihood method, we try to find the value of mu and sigma or some estimator of mu and sigma by maximizing the likelihood. This is typically what we do. In Bayesian estimation, the philosophy is slightly different. Actually, a whole lot of different. Bayesian estimation, they make one additional layer of assumption. The assumption is theta is continuous. Typically, in this, I'm just saying here, this continuous random variable. Actually, not, I better suggest theta is random variable. Not continuous. Continuous is not necessary. Theta is random variable. Random variable. Okay. Now, as soon as I say it's not only continuous variable, or it is actually a random variable, that means basically it immediately says theta has its own probability distribution. Theta follow a distribution, a probability distribution, some kind of pi theta, where pi is known as prior probability distribution. Okay. Now, this is one additional layer of complexity. It seems like it's a one additional layer of complexity we are adding here in the Bayesian estimation, but it's actually brings a lot more structure to the problem, and we will see how. So we are assuming theta has its own distribution. Then typically what we do is we say that, all right, can we let's apply Bayes theorem in that. How can we do that? The first thing we can think of, so if you apply Bayes theorem, and using Bayes theorem, what can I do is, if I can try to come up with a conditional probability distribution, where I'm saying that given the data, how theta behaves. Okay, so what I can do, I can just say that, all right, this is on that, if this is a conditional probability, I can write it using Bayes theorem, this conditional probability of f of x tilde given theta times pi of theta divided by integration over theta f of x tilde given theta times pi of theta times t of theta. Okay. So we are interested in this. This is something called posterior probability distribution. So posterior probability distribution. So the idea is I have some idea about the theta, suppose, and suppose this is called prior probability distribution. This is my prior probability distribution over theta. Now I observe x tilde. As soon as I observe my x tilde, I update my probability distribution over theta, and suppose it turns out something like that. Much more sharper. I'm saying that most likely my theta is somewhere here with a much more probability. Now, previously I didn't have much confidence, so it is like slightly flatter probably, but now I have seen x tilde. So now this is prior, this was a prior probability of prior belief, and at that time I was thinking like, okay, maybe theta is here, but now theta turns out to be probably here. So this is typically the posterior probability. Okay, so this is the nutshell, the idea of what Bayes estimation does. I'll go into the more nitty gritty, but this is like 30,000 feet overview of what Bayes estimation or Bayes estimator does, try to do. Anybody have any question here?
Sir, in this course, are we going to look into Bayesian statistics?
No, not really. Not really. I'm just going to gently touch one or two lecture on this. That's it. So that I just established some connection between the Bayesian estimation and likelihood estimation, so that I think whatever is required whatever will be required in your machine learning and DMML and advanced machine learning and predictive analytics, these three courses, not more than that. So that will be maybe one lecture, max two lecture, not more than that. Okay.
Thank you, sir.
So this is like 30,000 feet view of what Bayesian estimation does. Now, note that here is one interesting thing. This object, you know this object. Can you tell me what is this object? Any idea? Actually, actually this is nothing but likelihood function, right? Because given theta, whatever my observed x evaluated at the density. So this is what we do. This is another notational way of writing. Okay, this is a joint density of x tildes given the theta, and then we are writing it as a product, and then typically we use this popular notation of L theta given x tilde to emphasize more on the theta, but actually proper notation or representation is this f of x tilde given theta. So what I am doing then, my effectively, I have a prior distribution on the theta, and then I am kind of marrying the prior distribution with the likelihood function through the Bayes theorem. Okay, I'm developing a posterior distribution, but posterior distribution is just not enough, because posterior distribution is not going to give me the estimates for theta. End of the day, I need a value for theta. How can I get the value for theta? As soon as I get a posterior distribution, I can calculate this expected value of theta given x tilde, which is typically called posterior mean. Okay, so posterior mean is integration theta times posterior distribution theta given x tilde d theta. So this will be some function of tilde. So this will be my Bayes estimator posterior mean for, and if I want to estimate theta, so that this will be the posterior mean with respect to the posterior distribution pi. If I'm interested in, say, some functions of, say, h of theta given x tilde, then what I will do, I'll solve this integration problem, h of theta pi of theta given x tilde d theta. Now, as I'm integrating out theta, it will be some function of only data supposed to be, which I will use, which we can say that some that will estimate the h of theta. Like if I'm interested in theta square or theta cube, okay. So this is my posterior mean. Posterior mean is some estimate of theta. I want to estimate. Another thing I can use is posterior mode. Okay, so the posterior mode theta hat is arc max of theta in theta over posterior distribution. So you take the posterior distribution and try to find the theta where the posterior mode is. So this is my posterior distribution, right? So this is my posterior distribution. I'll try to find where the posterior distribution is highest. Corresponding value is my posterior mode. Okay, so this will be my posterior mode, and I can use that also as my estimate of theta. So either I can use posterior mean or I can use posterior mode. So that immediately gives me two Bayes estimator for theta. You can ask me, can I use posterior median? I say yes, why not? You can compute posterior median. That can also be used as an estimator. So in one shot, I give you three estimator. Okay. So which is basically what is that? Some function from. So basically, you have to solve this. You have to solve this theta median by theta given x tilde d theta for which value it is half. This integration is half. So basically you want theta less than theta median given the data. This posterior probability is half. You figure out and then you get you solve this equation, you get the thing. Okay. Now, so before we take some example, and that will make it more clear how we solve the Bayes estimation problem, I just want you to figure out that I never spoke about the dimension of theta. Here I have taken a couple of examples where one example theta is one dimension, another second example it is two dimension. Technically, when we are developing this Bayesian estimation method, we are not talking about the dimension of theta. Theta could be high dimension, like 5, 6, 7 p dimension we can think of. Okay. Now, problem will be that does this mean I have to solve effectively this one? This is a 5-dimension problem. This integration, solving this integration is a 5-dimension. If it is my theta is 5-dimension, solving this integration 5-dimension problem, answer is yes. Similarly, if I want to find the posterior median, is it going to be a 5-dimension problem? The answer is yes. So oftentimes solving these integration turns out to be quite high dimension integration. You don't have analytically closed form solution most of the time. Very rarely you will find for some straightforward probability models, you will have mathematically closed form solution, but most of the time you will not have a mathematically closed form solution. What you will have is some kind of mathematical form, which is a functional form, which you cannot solve. You will start, and in the midway, you will see that you will not be able to progress anymore. At that time, you have to solve this integration using numerical integration technique. And their Monte Carlo technique, Markov chain Monte Carlo technique comes handy to solve this high dimension integration. So another approach is then why don't we solve this problem? Because we are very good at optimization, we can solve the posterior mode problem using optimization technique. Okay. And turns out that in the machine learning community, 99% problems are solved using this posterior mode technique, the optimization technique. Most of the deep learning neural network models, machine learning models like support vector machine, etc., 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 you will find the solutions are developed using the optimization technique. They either try to estimate the likelihood method using likelihood method or posterior mode method. They are being tried to solve those problems using either maximum likelihood estimates or the posterior mode using an optimization problem, solving this optimization problem to get the posterior mode. But if you want to do a full-blown Bayesian estimation methods, a Bayesian inference method, you have to learn the Markov chain Monte Carlo method as well. So Markov chain Monte Carlo was developed mostly by the physicists to solve high dimension integration problem. And then later on, many statisticians, after I think 90s onwards, many statisticians had realized that the Bayes problem can be solved using MCMC, and a lot of Bayesian statisticians have contributed in this literature, MCMC literature, which essentially solve this high dimensional integration problem. Okay, this is the fundamental difference. Either you have to solve the Bayesian solution in order to get the value of theta, either you have to go through this Bayesian solution using MCMC, to solve this integration, high dimensional integration problem, or you have to solve this optimization problem where to get the final solution. Okay, now we will take an example. And this example is something like this. So I'll tell you this example with a small story, and then it will make much more sense to you. The story goes like this. I don't know it is true or false, but the story goes like this, that around 1700 period, when there are in the science there are two approach. One is called deductive approach, another is called inductive approach. Deductive approach, another is called inductive approach. From the name it is pretty much clear what I mean by deductive and inductive. So the deductive approach is where you have certain rules and assumptions, and then from the assumptions it follows the theorems and the results and lemma. All these things automatically, the entire theory gets deducted. In the inductive approach, it look into certain observations. Then it tries to find some pattern. And then it sees more observation. And then it sees more observation. In each observation, if the pattern repeats, and then finally you develop the sense that this thing happens. You conclude that pattern is permanent. Okay, so it's like more data oriented. Like you have a hypothesis, you collect some pattern data, see in that data if you have that pattern, and then you collect few more data points, and then you collect few more data points, and you collect few more data points, and you keep seeing that the pattern persists, and then you decide that, okay, there is a systematic problem or systematic pattern is permanent pattern. Let me give you an example. For there is a hypothesis that, okay, systematically number of girl student in CMI is less than the boy student. Okay, so I will begin with this assumption. To begin with, I will say it is a hypothesis. Then what I will do, I will take this year's students roster and I'll see how many boys and how many girls are there. Okay, that emerges a pattern. Then I'll go to the last year's roster. And then again, if the same pattern persists, then I'll go to the older days. And in all these years, if the same pattern persists, then I will conclude this pattern is permanent. The problem with this inductive approach was this is the typical approach, but the scientists in 1700 and 1800, they were not particularly the people who were in math and physics, mostly from the physics, they were not very happy with this kind of approach, because their argument was that if sun rises from east for last 1 million years, that does not lead us to conclude that sun will rise tomorrow from the east. Okay, so they have a kind of very extreme statement. In order to solve that problem, Bayes give actually this is from Bayes' um, paper. He gave this idea that okay, xi is sun equal to 1 if sun rises from east with probability p. P is between 0 and 1 and 0 otherwise. So some xi, basically Bernoulli p 0 less than p less than 1, and I have seen these pattern for last n days. Okay, then what happens? Then he says that okay, let's assume that I have no clue where the p is, so I assume p follow uniform 0 1. Okay, if that is so, then can I write the f of, now let us look into the Bayes theorem. So Bayes theorem, what I need first, I need this f of x tilde theta. So what is my f of x tilde theta? X tilde p is product equal to 1 to n p to the power xi 1 minus p to the power 1 minus xi. Okay, so basically I can write p to the power summation xi 1 minus p to the power n minus summation xi 1 to n 1 to n. Now, so that means posterior distribution of p given x tilde is f of x tilde given p times pi of p integration 0 to 1 f of x tilde given p pi of p d of p. Now pi of p is 1 between in the range 0 to 1 and 0 otherwise. Okay, so that makes our life easier. So this is p to the power summation xi 1 minus p to the power n minus summation xi. Okay, times 1 makes my life simpler, and this is p to the power summation xi 1 minus p to the power n minus summation xi dp. Now let us call summation xi as say t, okay, to make our life little simpler. So p to the power t 1 minus p to the power n minus t divided by 0 to 1 p to the power t 1 minus p to the power n minus t dp. Okay, now can anybody tell me what will be the solution of this integration. This is a simple, very known integration.
Sir, it's beta integral, I think.
Correct. This is a beta integral. P to the power t 1 minus p to the power n minus t. This is a beta integral with t plus 1, because you can write basically t plus 1 minus 1, and this is n minus t plus 1 minus 1. You can write it in this way. So it will be n minus t plus 1. Okay. Are all of you with me? So what is, it turns out that means this posterior distribution of P follow beta posterior of P follow beta distribution with T plus 1 comma n minus T plus 1. Fine. Then what is the expected value of beta distribution? P given the T is, remember that T is the summation xi, which is sufficient statistic for P, right? So my posterior distribution turns out to be some function of sufficient statistic. Turns out posterior distribution of beta distribution will be, if the result we will use is for beta distribution, if P follow beta AB, then expected value of P, you can take it cross check with any textbook, typically A by A plus B. So it will be T plus 1 by n minus T plus 1 plus T plus 1. So this T cancels. So it will be T plus 1 by n plus 2, right? Now, what Bayes argued that for last, Bayes argued that for last n days, in many days, sun rises from east. So that means effectively I have observed t equal to n. So that means expected value of p given t equal to n is n plus 1 by n plus 2. Now, if n is 1 million days, I can say that expected value of p is given the t, given the data, given that we are observing it for so many years, is approximately 1. So that means sun will rise from east with probability 1. Okay, so that's what Bayes argued, that how, so he tries to give sort of a probabilistic, he tries to develop a probabilistic framework to argue certain scientific pattern in favor of certain scientific pattern. So when I will have only, if I see I have only last 7 days sun rises from east, then it will be 7 plus 1 by 7 plus 2. It will be like 0.99 kind of thing. But, and as we keep observing more and more and more days, so my pattern will become more and more and more concrete. So this was one of the argument by Bayes. Then another interesting example that I was introduced, that suppose X follow only, you have only one observation, X follow Bernoulli P. Okay. What is the, how you estimate P based on one observation? How you estimate P based on one observation? Based on one observation. So fine. Now my n is 1. I can argue that expected value of P. So effectively in MLE will be P hat equal to X, because MLE we do know that X P hat is X by N is equal to 1, so it will be all thing is X. Now X can take value either 0 or 1 with probability 1 minus P and with probability P. So that means P hat will be either 0 or 1. The value of P hat will be either 0 or 1. But look at the range of P. It does not include neither 0 nor 1. So if you have only single observation, then MLE is not a valid answer. MLE is not valid. MLE is not valid at all. But look at the Bayes estimate. Expected value of P given T is effectively T plus N by N plus 2. So that means what is my T? T is summation xi 1 to N. My N is 1. So basically T is my X and N is 1. So I'm getting X plus 1 by 2. Now, if we observe,
Sir, n is 1, so it will be 3, I guess, the denominator.
correct. Yeah. If we observe X equal to 0, then my Bayes estimate is 1 by 3. And if we observe X equal to 1, then my Bayes estimate is 2 by 3. Both are in the feasible range of P. So Bayes estimate is a valid solution. But likelihood turns out to be not a valid solution. So it's a sort of a corner problem. It's a very small toy problem, but it's an interesting argument that was developed when theory gets developed, basically. Okay. So I am going to quickly, so here I have developed everything based on the one prior distribution, uniform 0, 1. Turns out uniform 0, 1 is a special case of beta distribution. Uniform 0, 1 is a special case of beta distribution when beta is 1, 1. So I can take prior instead of beta 1, 1 as my, so if you take beta 1, 1, you will get exactly same answers. Basically, uniform 0, 1 is special case of beta 1, 1 distribution. So I can take prior distribution as beta distribution with parameter A and B. If I try that, turns out the rest of the thing exactly same. So it will be my P given conditional posterior distribution is P to the power T 1 minus P to the power N minus T. Now the PDF of beta distribution is P to the power A minus 1, 1 minus P to the power B minus 1. So this will be integration 0 to 1 P to the power T plus A minus 1, 1 minus P to the power N plus B minus T minus 1 D of P. So this turns out to be the beta distribution of T plus A N plus B minus T, P to the power T plus A minus 1, I can write 1 minus P to the power N plus B minus T, okay? So that means my posterior distribution of P given X tilde is effectively following beta distribution T plus A comma N plus B minus T. Now turns out posterior distribution of XP given X tilde is T plus A N plus B minus T plus T plus A. So this T cancels. So turns out T plus A by N plus B plus A. Now this I can write as something like this. N by N plus B plus A times T by N plus A plus B by N plus A plus B times A by A plus B. Is that okay with you guys?
Yes, sir.
Fine. Do you see an interesting pattern here? Look, very interesting pattern is
The weighted sum of expectations side of beta
correct.
distributions.
Correct. Wait, not really. I'll tell you what. This guy, what is this guy? He is maximum likelihood estimate of P. Correct? And who is this guy? This is prior mean of P. So remember that if I'm assuming P is follow beta distribution, my prior distribution. So prior mean is expected value of P, which is A by A plus P. Okay. And this I can write as weight depending on, so I can write it as omega over T by N times 1 minus omega times A by A plus B, where omega is N by N plus B plus A, because 1 minus omega will give me this A plus. So this is my 1 minus omega and this is omega. Okay. So, so turns out posterior mean is,
Sir, your voice. Very-
sorry, can you hear me now?
Yes.
Posterior mean is the weighted average of maximum likelihood estimate and prior mean. Okay, so that means suppose 0 is here, 1 is here. My first, suppose my I have taken say beta 2 2. Okay, say beta 2 comma 2 is my prior distribution. So this will be typically, it looks something like that. Now I have seen my p hat, my MLE, p hat MLE is say 0.7. So somewhere this is half. So this is my prior mean. This is prior mean. And my MLE is 0.7. So suppose this is 0.7. This is my MLE. So my posterior mean will be somewhere, since it's a weighted average between MLE and prior mean, I can expect it will be somewhere in this region, in this between the two. So suppose this is where the MLE is, posterior mean is. Okay. So the posterior mean, that means will be something like this, or posterior distribution will be something like this. Okay, where most of the mass will be hovering around the posterior mean. Okay, so this is the idea of how the Bayes estimators works. Okay.
So, sir, this also gives us a lower and upper bound for the posterior mean.
Posterior mean, yes, yes, yes. Two more point and then I will close today's discussion on Bayesian estimation. So, if you look into the posterior mean, let's look into the posterior mean for sample proportion a little bit more detail. So P, expected value of P given X tilde, let us look into it once more. So it is N by N plus B plus A times T by N plus A plus B by N, A plus B by N, A plus B divided by A plus B. Now if you look as N goes to infinity, what happens? When I'm saying N goes to infinity, means sample size increases. As sample size increases, A plus B by N plus A plus B, this will go to 0 because A and B is constant. So naturally it will go to 0. If this goes to 0, this entire part goes to 0. What happened to this part? So N by N plus B plus A, this guy go to 1. So as N tends to infinity, my posterior mean will eventually converge to MLE. That means as I'm seeing more and more sample, the effect of my prior belief or prior distribution will be washed out, and finally my final answer will be completely driven by the data. And so my posterior mean, my Bayes estimator, will converge to the likelihood estimator. So that means if I have lots and lots of data, my posterior mean or the Bayes estimator and the maximum likelihood estimator will be very close to each other. Okay, so this is a extremely important properties of Bayesian estimation. Sometimes it's called the Bayesian consistency. Bayesian consistency means as you see more and more data, your the effect of your prior distribution should wash out, and your posterior analysis will eventually converge to the likelihood analysis. So as you see more data, more and more effect of Bayesian effect of prior will wash out, and posterior analysis should conform with likelihood analysis. Okay, so this is a very important thing, that if you have enough data, that finally the likelihood analysis, frequencies and Bayesian, they should conform to the same analysis, same final thing, and they should not differ. So main advantage actually lies when you have a high dimension problem. That means you have too many parameter and too little data. And there Bayesian analysis turns out to be very useful. That if you have too many parameters and too little data, for example, in this is a, even if it is a toy, it was a toy example, you have one parameter and one observation. And that one observation was not enough to give you a valid analysis for P. But what we did, we made one structural assumption that P is somewhere is following uniform 0, 1. Okay. if you assume this P is following uniform 0, 1, that one structural assumption gives you this nice solution. So sometimes you can make some structural assumption, like if you're doing an optimization problem, and suppose the optimization does not have a feasible solution. Okay, if your optimization problem does not have a feasible solution, then what you can do, you can try to define certain constraint, and you will see that under certain constraint your optimization will have a nice solution. And we will see this in the next lecture. We will see that this constraint optimization is actually nothing but turns out to be Bayesian solution. Okay, so next week we will explore the couple of things. One is we will do some example, but you can try to explore by yourself also. Couple of things is, one is relationship between MLE and posterior mode. And second is, we will see that oftentimes not oftentimes, let's say constrained optimization, the relationship between constrained optimization and Bayes solution. Before I go, I'll just take 2 more minutes. I just want to discuss a small thing. You notice that we started with Bernoulli P. Then we said that if I take P follow beta distribution with A comma B, turns out this is my likelihood, this is my prior, and when we apply Bayes theorem on that, we got posterior P given X tilde also follow beta distribution, which is A plus T and N plus A N plus B minus T. N plus B minus T. You notice this prior and posterior belongs to same family of distribution. Same family of distribution. And this is a very interesting property, because if you know if you have a likelihood for which, if you can construct a known distribution for which posterior also belongs to the same family of distribution, such prior distribution is known as conjugate prior. Okay. So all we have to do then, just figure out the parameters of that distribution, conjugate prior. And conjugate prior actually makes our life much more simpler. Okay, and we will see that for Poisson distribution also, you have to find certain, you will have some conjugate prior. For normal distribution also, you will have some conjugate prior. Exponential also you have some. For some probability models, you have the conjugate prior. not for all. Most of the time you don't, very complicated model, you don't have a conjugate prior, but most, at least for the basic models, you do have the conjugate priors. And these conjugate priors sometimes makes our life much simpler, but beyond that we will not discuss here. So I'll stop here, and next week we will discuss little bit more on the, not the entire discussion, some discussion on the Bayesian estimation, and then we will move on to the next major topic on evaluating next section actually of this chapter, evaluating the estimators, that how I know. So I got a likelihood estimator and I got a Bayes estimator. How do I know which one is better? Okay, so that we will start discussing that which one to use and why to use, when which we should not use, and stuff like that. Okay. All right. Anybody have any question? All right. If you don't have any question, then we can end the class here, and we can meet next week again. Well, next week is your exam week.
Sir, nothing of that sort has been announced. Like just
Okay.
one course has one instructor has instructed us about the mid
Okay.
semester.
Okay. All right. Then if you don't have any problem, then we can continue next week also. All right, then next Saturday. I know that last week lecture I did not upload it. So today I'll try to upload all the lectures, including the visualization also. Okay. So today afternoon I'll do that.
Okay.
Okay. Bye.
Bye.
Bye.